When I was a lecturer at UQ for undergraduate engineering, they wanted me to give a talk on sustainability of mining. And so they gave me an example of what CSIRO had done and what UQ had done in the past. And there was nothing in them. It really upset me. And they said, you have to give one. So I went out and collected my own information. And what you see today is an outcome of that. The basic upshot is mining is not really sustainable. When they said mining sustainable, they got the wrong t-shirt. What they really meant was, we took money from the government and did a reasonable job. Let me show you why I think that. The Earth is a global system and it's a finite system. It's been stable for some time. It dynamically regulates itself, but it's not growing. Us, on the other hand, are growing. Our population has increased and our energy sector is all non-renewable. But I'm going to talk to you about this bit in the centre. Per capita, each and every one of us has increased 8.6 times, I think it's a little higher than that now, of our demands on the energy sector per capita. So where does all this stuff come from? Mining consumes close to 10% of the world's energy, creates a lot of the pollution, threatens a large tract of the natural environment, and creates only a small share of jobs. But what it also does is empowers everything else. It supplies raw materials for everything. Anyone who drives a car, anyone who uses a computer, anyone who works in a building that's made of concrete or steel is an active participant in the mining process. Put this into context though, if your gold ring on your finger, there's about 3 tons of waste sitting on a mullet heap somewhere. Mining is all about money. Now, beyond the obvious, let me explain why this is relevant. They use a process called net present value to value their projects. What that is money returned now or next week is worth much more than money returned, say, in 5 years' time in risk terms. That esoteric concept has been translated into a real, tangible value. So financial return over time is discounted. And the faster you rip it out of the ground and process it, the better. The banks get their money back. So high grading a deposit is good business. Now we talk about natural resources and effective use of it. That's not what this is about. Mining is about money, right? So we will leave behind low-grade material that's perfectly usable in context of making more money. So low-grade material, it's often economic, is dumped on the waste heap. Leaving low-grade material behind is called sterilised. It's considered good business as it raises NPV. So deposits are not exploited efficiently based on their metal content. They're exploited in terms of economic efficiency. This graph is what the mining industry has got itself in a twist over the last couple of years. Multi-factor productivity index has decreased by 40-something%. What that is 40% more work has gone in to get the same unit of metal out of the ground. Capital, labour, materials, services, energy. What that means is it's not as viable economically. And here's why. As grade decreases, there's an exponential relationship, because that's the way geology works in this context. Once you actually get below a certain grade, you've got much, much more tons to shift to get the same amount of metal. Now let me elaborate. In the 1800s, when the Europeans settled the United States continent, there was no industrialization as we know it there. And they found, among other things, large boulders of natural copper, pure copper, like what these two guys are sitting on, in stream beds. So they ripped all those out and they processed them. And then they went as far as processing nuggets in streams. And then when they got rid of those and they used all those up, they go, oh, the horror, they've got to dig it out of the ground now. And there's lots of news articles at the time that miners complaining that they've got to dig it up out of the ground and the grade is as low as 15%. And this is where we are now. Bingham Canyon in Connecticut United States, Salt Lake City. The grade, depending on what part of the pit you're in, is between 0.2 and 0.57%. A spectacular display of the use of energy. This is what we're doing. Humans, like most other biological organisms, use the highest quality, richest and easier to obtain resources first, where the first half is consumed very quickly, but the second half is consumed first half takes a long time to consume, and the second half is consumed quickly. This is what we're doing. So over time, this is copper. This is the copper case study. The grade of copper is this line down here. It's been dropping. We've been taking in all the good deposits first, but demand has been going up. And so there's a squeeze on technological solutions, and we actually don't know what we're going to do at this time. But it's also happening with all mining. All grade is lowering. We're not growing new deposits, Your Honour. But production, on the other hand, in the name of economic growth, is going through the roof. And here's how we've done that. 100 years or so ago, mining was actually done by horse and cart, carting rock from the pit face. And that's how we do it now. Same principle, but the toys are bigger. Economies of scale, engineering, energy-based. But there's a number of other patterns happening too. Among other things, we have processed all the easy-to-work deposits, and what's left now is the harder-to-work ones. This is impact breakage. The higher the index it is, the softer it is. And so the number of tests that have been looked at, this is a database of 3,000 tests. The rock being tested has indeed gotten harder. What does it mean? More power draws now required to run the same piece of rock through the mill. Now, each of these mining plants is going to be designed to a specific set of specifications. How hard the rock is, how fine they have to grind it to, how many 1,000 tonnes an hour they have to process. Target grind size is how fine we have to grind the rock, and that has been decreasing over time too. To explain this, let's say we have air intact rock here. Through the breakage process, it's broken down to the point where our target mineral is what we call liberated. 50 years ago or 40 years ago, your target ore size typically was around 150 odd micron. But now, increasingly, we're having to go to, say, 4 or 5 micron. Here's what's happening. There is an energy relationship called the Hooke relationship, where as you go smaller and smaller, much more energy is required to put it in. It's also an exponential relationship. So a decrease in grain size in the mineralogy translates into an engineering decrease in the final size, what's called P80, or the product 80% passes, and which is an exponential increase in required power draw. On every front, more power is required. We dug up all the good stuff, and now we're left trying to work with the low-grade horrible deposits in increasingly challenging postcodes. Now, to add insult to injury, the number of deposits being discovered is also falling. Most of the new operations being brought online there are not what we call greenfield operations, but expansions of old ventures. Data is still being collected on this one, but most of the deposits on the ground at the moment are what we call economically marginal. This is a quote from someone who has done more to develop mining technology than anyone else I can think of. And he said this when asked a curly question in this nature: "There is no need to concern yourself about decreasing copper grade and mining sustainability. The entire Andes mountain range in South America is one big gigantic copper deposit. Yeah, let's mine it. With some areas more concentrated than others. Yes, costs of mining are going up, but they can be merely passed on to the consumer through rising metal price. The world always has and always will need copper. And as grade gets lower, we'll just mine more tons, and mining will never end. The economics will be forced to keep up." Now this is how we've thought about this in this industry. We're very conservative. It's how we see each other. It's how we talk. It's how we problem solve. And yes, it will evolve. The question is into what? And this is where we're going. The goalposts are shifting. The deposits being looked at now for the next generation are huge, much larger than we've seen before. Penalty elements like arsenic and cyanide and asbestos, stuff that we wouldn't have touched with a barge pole a few decades ago, are now considered normal. What makes a lot of this viable is China is prepared to take and process stuff that no one else will. Ever decreasing grind sizes, and the operating on an economy of a scale never seen before. One operation in Pakistan conceptually was talking about 4 million tonnes a day of blasted rock, about 40% of which is ore. And technically there's a lot of problems with that, but the size of that operation is extraordinary. And to stay economically viable, the economics of scale have to be applied. Operations will double and triple in size. That's what they think, and that's what they believe, and that's what they're planning for. What's interesting is all of this is based on the assumption that there is no energy or water shortage. Can't possibly happen. Now let's look at the demand side of things. Demand is going up. Around 1920, the average copper grade was around 1.6%, and now it's about 0.5%. So let's look at that. Demand now, well, this is about 2010, is 17 million tonnes of copper metal a year. So we're talking 3.4 billion tonnes of rock has to be shifted. And current estimations for demand for copper will increase to about 100 million tonnes by, say, 2100. It's a projection, but it's a reasonable one based on past behaviour. And in that projection, historically over the last 23 years have accounted for half of all the copper ever mined. And the next 24 years will exceed all the copper ever mined. So, if we're going to continue with, say, 100 million tonnes of demand a year, and the grade is, say, 0.5%, we're talking 20 billion tonnes of rock, a year. And if that grade was to decrease to, say, 0.2%, which is already being looked at, that's 50 billion tonnes a year. So, is it sustainable? Now, what does the mining industry think it's going to do about this? In terms of problem solving, at the moment we'll just make the economic case, and it's either a business case for it or not, and if it's not viable, we'll ignore it and come back to it later. But if you back them into a corner, they've come up with the following solutions. Apply economies of scale, bigger and bigger and bigger. These little dots here are those big mining trucks. And already in the next generation, it's 2 and 3 times the size of existing operations, and the generation after that will have to be bigger again. At the moment, the limit of engineering technology can go down to about 3 kilometres deep. So now we're going to start considering, say, 3 to 5 kilometres or deeper. And then they say, well, there's only one planet, and if we mine it out, let's go find another one. And this was tongue-in-cheek, but it was actually written down. This is actually what they suggested. We'll go and mine Mars or the Moon, right? Well, the other one that was suggested that made me laugh was, let's go out to the asteroid belt, lasso an asteroid, bring it back to Earth, and get it into a low orbit, and then drop it into the desert somewhere and process it. Can't see this backfiring at all. Yeah. This is the most challenging option, and that's mining under the sea. The salt water is highly corrosive. Sea currents also shift things around and also operating at underwater pressure. That's why we haven't really done it yet. It's actually the most technological challenging. And that brings us neatly to energy. Now, mining industry, if you do take the time to tell them about things like peak oil, peak gas, or whatever, they say, oh, we've heard these predictions before. Or the other one is, we'll care when someone pays us to care. I'm serious. That's their attitude. From an operating point of view, power consumption is about 10%. And on any given mine site, you do have bigger things to worry about. And if the cost of energy doubles, or just transferred on to the customer. That's the general consensus. Here's energy consumption in your average mining operation. Most of it is natural gas. Gas is piped in and we'll have, say, a power station. You've got automotive diesel, truck and shovel fleets, and you've got electricity that's usually coal. Now the takeaway point here is energy consumption from about, say, 1973 to about 2008 has increased 450%. Energy is going up. So let's look at some of these resources. Coal. This is a study that's been done. There's a few interesting reports which have been released. This is one. A couple of reports I've seen, they've got the date around 2020. 7 years away. Now that should concern any thinking politician. What are they going to do when the coal grid goes offline? Oil. Well, here's our regular conventional oil. For every barrel of oil that we discover now, we're using 3 or 4, or 4 or 5, depending on which analyst you look at. There's a more updated version of that graph. I saw this graph as an undergraduate geologist in 1992. I didn't understand it at the time, its implications. So if you put things like tar sands and oil shale and what have you, conventional oil peaked in 2006, but total oil production is slated to peak around 2012, just past, around now. The reason we're not really feeling the pain for it at the moment is demand destruction has been happening in the form of economic chaos. Peak oil happened in 2006 for conventional oil. So let's stick the boot in. This is oil production. And it rose and it's plateaued around 2004-2005. At that point, oil was $50 a barrel. And it got to there and oil was almost 3 times the price. And then we had the GFC. Here's another graph. The spot price of oil versus crude production. It had one kind of behaviour up to around 2005, then past that it had a very different behaviour. And that point is the same across there. In this window here, supply was elastic, it could meet demand, not a problem at all. In this window here, it was inelastic. If you were to take a mining professional and tell them about peak oil, they said, well, it's not a problem, it's retail. You know, we use our power out of gas or truck and shovels and what have you. Yeah, just look at that. Ore is shifted in big trucks run on diesel. These trucks have a capacity of around 250 tonnes per load. But if I was to say you're not allowed to use diesel anymore, but you've got to meet your engineering targets, what are your options? All right, we're going to move this with donkeys. Right, donkeys shift, say, about 200 kilos a donkey. That's a lot. That's a big donkey. But one truckload is 3,400 donkey loads. Now, Bingham Canyon, you want 5,000 tonnes an hour of rock. 66,000 donkey loads an hour. Some of these larger mine sites, like Escalating, for example, Big Super Pits, 1/3 of the total energy cost is consumed getting the ore from the pit floor up to the plant. There comes a point when the cost of dealing with the waste is going to exceed the cost or the value of the metal. Economics can't solve everything. So let's look at the cost of mining versus the cost of oil. Here's the price of oil. It peaks, it drops, and it's rising again. Here's the cost of production of potash and iron ore. Same pattern. Now let's stick the boot in. The GFC happened there, there, and there. Not economically viable, everything crashes. We're a petroleum-based economy on the industrialization scale as well as retail. There it is. Now, how will corporate culture and government behave on managing a needed resource in an era of scarcity? Let's look at coal seam gas. I don't know about here, but where I live in Brisbane, around the region, CSG is a bit of a problem. Some of the locals on the ground. Four Corners did a very good presentation a couple of months ago which actually looked at this. Every CSG project that has gone through the system has been pushed through very, very quickly, and all of them were accepted. And if due process was actually properly followed, then the majority of the projects would have been rejected. Private companies and governments have colluded on the ground at the expense of the people on the ground. That's the charge. Of course, that's been debated. What the people on the ground do find, though, is they have an enormous amount of resources arrayed against them. Legal and political resources to ramrod this through. It's all right, trust me. It'll be all good, we'll make you rich. Concerns of the people on the ground are the loss of drinking water, environmental pollution in the whole region where they live and where they earn their livelihood. And the charge is state governments that are bankrupt and desperate for revenue have sold out to the public in exchange for a mining royalties revenue stream. Hotly debated, but that's also my opinion. And here is why it's happening. What's interesting is the Four Corners program did not make this connection. Why would the government take an extraordinary risk for its mandate to be questioned? Peak gas, when you put everything together, conventional and unconventional, is around 2018. 5 years away. You're not going to tell me that this is an unknown set of circumstances. If you put the unconventional stuff like CSG and shale gas into this equation, peak gas has been pushed back from around 2011. There you have it. That is why. Uranium. A friend of mine who works at BHP, I backed him into the corner and plied him with alcohol. I said, look, what are you going to do if you have energy go offline? Oh, easy, no problem. We'll just put a small-scale nuclear reactor in every mine site. Can't be done. Right, let's look at that. There's probably enough uranium for existing power stations. Nuclear power does have its place, but can it replace our existing energy infrastructure? Well, if you do a future projection on known uranium reserves, where that's about where we are now, yes, you can increase production, and then it'll peak and drop off over the next couple of decades. It's a non-renewable resource just like anything else. But if nuclear power would have to increase 12 to 13 times at the peak capacity potential, not even where we are now, just to supply enough power to the grid to replace fossil fuels. But our existing infrastructure needs to be replaced because it's aging. This red dotted line is if things just decommission at the time when they're supposed to be, power consumption, power production will just drop off. And new construction and new sites need to be developed. But if that has to increase 12 to 13 times and then maintain that for the next 50 to 60 years, someone's going to pay for it, which at the moment is a bit of a problem. It takes about 5 years to build a nuclear power station or any industrial structure like that, which means, if you look at the numbers, that capability has to be online and operational in, say, 4 or 5 years. Good luck with that. Nuclear power, though, does have a number of Achilles heels, and this is one. Spent fuel rods. Once nuclear power is, uranium rods are used, they can't just be thrown away in the local rubbish tip. They've got to be stored. They're highly radioactive. They're very hot. And they're required to be stored underwater in cooling facilities that require power to run. And this has to happen for 10 to 20 years, and then they're put in dry storage. In the United States alone, these are the commercial spent nuclear fuel storage sites. Now that's just what we have now. Imagine 12 to 13 times this. When all the energy is peaked, by the time uranium peaks, oil will be gone, gas will be gone, and coal will be gone. Or not gone, depleted. They will not be able to generate large amounts of power. So when uranium peaks and declines, all those new spent power rods have to be stored in a way that require considerable power requirements. And this will be needed for 10 to 20 years after they're used. And if we don't do it, you've got considerable radiation pollution problems. That's a problem. And until someone comes up with a solution, I don't think nuclear is viable. There's a number of other problems. Most industrial structures have been authorised based on a risk probability matrix, based on what's been happening for the last 200 years in terms of natural disasters. But there's this thing called climate change, which is changing the rules. Here is a seismic hazard map. The darker the colour, the higher the risk. Over the top of that is positions to nuclear power plants. As you can see, there are a number of them in seismically active zones. This picture is a road to the Fukushima plant in Japan. You're going to have a delicate and very sensitive structure, like a nuclear power plant. You're going to do that to its foundations and expect it to be viable after that. Right, that's another problem. But here's a really silly one. There are about 11 nuclear power plants on the banks of the Mississippi and Missouri rivers. In the area, the Mississippi River is actually protected by levee banks where the level of the river is considerably higher than the surrounding countryside. It's not just possible, it's probable. It's happened a couple of times where that levee system has failed, and when it does, the whole region floods. So when you've got cooling generators for operating reactors, if they're underwater, they're not going to run. June 2011, a couple of months after Fukushima, they almost had a second incident. This was the Fort Callahan nuclear power plant that flooded. Now, what's the intellectual giant that put a facility like that on the banks of a river that's actually not probable to flood? Yeah. And now for the last Achilles heel for nuclear as I see it. This is the Fukushima case study. For those who don't know, the Japanese coast was hit by an underwater earthquake, magnitude 9.0, very high. That triggered a tsunami, and that tsunami caused a lot of damage, among which level 7 meltdowns in multiple reactors. Now, I've got a problem with the official story here. This is the reactor setup, and this is what happened after the disaster. Here's a picture locally of where the tsunami has passed through. And as you can see, there's a lot of debris. Yes, that's a boat sitting on top of that building. Now have a look at this photo down here. You're not seeing the debris field. In front of these reactors, you're not seeing lots of debris sitting on these pipes, or in front of this building down here. There's intact vegetation around over here. I put to you that the damage in these reactors didn't happen by a big wave hitting them. They happened by an explosion that happened internally. That's what, in terms of photo forensics, that photo tells me. Now, there's two power sources in that reactor. One is the cooling system, but the other one is the reactor itself. If the cooling system blew up to cause that kind of damage from the inside out, then that reactor is not going to be cooled and it would melt down. The series of meltdowns happened due to a failure of coolant systems. The diesel generators, they were damaged by this tsunami itself, not the reactors itself. The coolant systems went offline. Here is a picture of one of the reactors exploding. Now, the official story says this explosion was due to the cooling system going up. It was a hydrogen-based system. Now, mass spectroscopy tells us hydrogen, at the temperature of this cloud, which would be about 1,000 degrees Kelvin, or thereabouts, should have a blue tint to it. There are 4 visible lines for hydrogen, 3 of them are blue. You have to get very hot to get the red tint. Plutonium, on the other hand, when you get to that level, has a yellow colour to it. This cloud, ladies and gentlemen, has a yellow tint to it. They've also admitted recently that the plutonium-based MOX fuel was in feed in these reactors. So I would suggest to you that that reactor has exploded and its core has been vented to the atmosphere. Now, this is a terrible accident. My point is this: the response of the local government and the response of the corporation tasked with actually running this facility have outright lied from the beginning, and they continue to do so. I call BS on the official story. I would say a compelling case can be made that we as a species are not mature enough to handle nuclear technology. What happens when there's an accident? What do we do about it? That right there is a problem. Now, let's put all those power sources together. You've got, on one graph, each power source is being unified with regard to the energy it brings to the power grid. Oil, natural gas, coal, and the layer across the top is uranium. Peak energy for everything is approximately 2017, 4 years away. Now, what happens to democracy and due process when there's not enough to go around with resources, as a necessary resource like energy? Back to mining. What does this mean? Energy is a problem. I haven't had time to do water, but water supply also is a problem. Power and water shortages clearly have a problem for mining, but decreasing grade requires more tons of rock to be shifted, which require more energy and more potable water to be used. Increasing ore hardness requires more power draw to crush and grind the ore, and decreasing grind size due to the mineralogy requires much more power draw. More water is needed per unit of extracted metal, and it's much more difficult to recycle when it's finer. More disseminated finer grain rocks are usually harder to crush and grind. But to remain economically viable, the operation has to double and triple in size. But demand is growing fast. Once these trends come together and the people on the ground actually understand what's happening, and they will, our civilization at large will have to be completely re-engineered, redesigned and reconstructed to a new set of rules. And it'll have to be done very quickly. And the only way we can do that is by mining more stuff than ever before. We just can't do it any other way. So what I was just saying there is mining will not end, but it'll be done according to a very different set of rules. It'll be administered very differently, and it will have a different mandate, and it probably won't involve money. Now, that would have got me professionally burned at the stake. For those of you who haven't had a laugh today, and you would like one, mining has a PR image with regard to sustainability. Now, I haven't actually seen this printed yet, but it's an opinion I've heard a couple of times, and I fell off my chair when I first heard this. Mining could be considered more sustainable than industrial agriculture, as there are more assets on the ground that will last for longer. Here's how this works. Every year, between 0.3 and 0.8% of global arable land disappear and is rendered unsuitable for agricultural production because of how we do it. About half our agricultural land is severely affected, and arable land loss is about 30 to 35 times the historical rate. Chemical fertilizers and herbicides are becoming less effective, and organic matter humus content has fallen from approximately 5% to 1% when it needs to be around 20%. And big ag uses 3 times the volume of potable water than mining. What we're trying to do here is say, it's us, it's them, it's them, it's them, stop giving us a hard time, please, please, please. Whiskey, Tango, Foxtrot. Now, for our industrial sectors to survive, if we were to do it right, we would have to do something like this. There's 2 possible paths. First, we'll call track transition. Let's say we've got, over time, mounting stress, drift, negotiation, people telling it's not a problem, and then we'll have an early crisis. Something will happen. More negotiation, but then we'll have an existential crisis, something that really changes everything. And what we'll do is we'll do something to save time. If we were talking finance, I'd be saying, this is what they do when they print money. We're kicking the can down the road. We're not actually fixing anything, in fact we're making it worse. But what we are doing is buying ourselves time. And we keep going down that loop until we're forced through that crisis point, and then we either write off and reset, and if we can't do that, we decay and collapse. The other one is room to manoeuvre. Let's go through the same process, mounting stress, negotiation, and we get to the crisis point. And then we sit down and think, gosh guys, we need to do something about this. So instead of going through all that other stuff, we're going to make a choice early enough in the piece where we can fundamentally reform how we do things. And we're onto a different path where we completely avoid the existential crisis. But that only is possible if we understand the true implications of the early crisis. The existential crisis in terms of the industrial sector, in my opinion, is energy. And peak energy, a couple of years away. That's everything. If we lose any one of the existing systems, we don't have the infrastructure to bring online immediately anyway. And I believe we're about there. Are we doing this up here? No. The early crisis, in my opinion, was the inelastic oil supply change in 2005, but that requires extraordinary leadership and vision, none of which is what we're seeing. But let's say they did do it, and we are seriously considering the problem. This model was developed by Hirsch in 2005 when we're looking at peak oil with regard to agricultural vulnerability. He came up with this wedge model, where you have a time where you're deciding what's your best replacement system and preparation. And once you've decided what the best system is, you've got to prepare for it, and then you've got to apply it, and it takes time to do that. He put down 20 years. The Beyond Zero's emission report says about 10 years. Either way, we're talking decades. But these problems are here now. We're a couple of years into this now. We're out of time. If we were to do this properly, we would have seriously discussed what to do around the mid-1980s and started applying the outcome by the late 1990s. And here we are in 2013. Each and every one of you would know exactly what that solution is, and you should be able to physically see it as you walk down the street. Yet we're still whining about whether there's a problem or not. This pattern can be applied to all our systems. It requires energy, manufacturing capability over and above standard demand, and large quantities of natural resources. Now, my wife asked me, when will this crash economically? She couldn't care less about the rest. She says, look, what are we talking about on the ground? The party's over when the demand for something vital outstrips supply, and some vital service completely ceases to function, or at least reliably. And the average people, en masse, understand that the world we live in is no longer possible. Peak oil is not the problem. Perception of peak oil is the flashpoint. And there's no easy solution that allows their life to continue in a fashion that they're accustomed to. At which point, it's on. Yeah. This is Chris Martin's 3E model. He breaks it down to three: the economy, energy, and environment. Our economy, the way it's set up, must grow exponentially. Our energy sector can't grow, and in fact is shrinking, and our environment is deteriorating heavily. The only thing that can change is the economy. And that's what we're seeing. We saw the GFC, and it was all made better by printing money. It's not going to fix anything. The industrial big picture looks like this. Decreasing grade plus decreasing grind size, which all require more power, and increasing depth, put together with peak energy. Also put together with the need of the expansion of production to stay viable, and we have peak mining. Rates of mining elements will peak and decline. But it's all about money. We can't do anything about money. So if we put sovereign debt default, fiat currency devaluation, credit freeze, and some kind of structural inflation, and the need to expansion of money needed to service that debt, that's peak finance. Now, I haven't said anything in here about this. I have a presentation kept aside. If anyone would like to start a bar fight, I can talk about that later. I personally think that each and every one of these things now has a possibility and a probability. Everyone should at least be discussing the possibility. It's probable. Are we? No. Right, so put these two together. We're no longer going to have the raw materials, and we won't be able to pay for them, which means we won't be making stuff anymore. Peak manufacturing. Put peak manufacturing with peak energy, and the idea of we now have a credit freeze, you can't pay for stuff, especially big stuff. We have peak industrialization. We're not going to see projects like the Hoover Dam anymore. We just won't be able to do it. Put those two together, and we have the end of the Industrial Revolution 160 years after it started. And ergo, we will see the end of materialism. The writing on the wall, for those of us walking down the street, everything we need and want to operate is drawn from non-renewable natural resources in a finite system. Most of those natural resources are depleting or will soon, and demand for everything we need or want is expanding fast. And when those trends meet, and they will, there will come a point when how we do things will change. And none of these things can be seen in isolation, so we're looking at a chain reaction. Richard Heinberg has put together an interesting thesis Real growth is dependent on energy and real resources, as opposed to numbers on a computer screen. And the price of oil to make exploration of oil economic and worthwhile is about $100 a barrel. Now, oil is energy, and energy allows us to do stuff and expand. The point past where expansion economically is very difficult is about $100 a barrel. Put those two together, and in macro terms, we've seen the end of growth. Now, some parts of the world will continue to grow, but if you look at it as a macro global system, growth will have plateaued around now, if we look back 20 years from now. But corporate culture must grow to survive. Our current business culture needs to show a profit. Anyone that doesn't show a profit of, say, 5 to 10% loses investment backing. And most businesses are not self-sufficient, and they need that investment to operate. The need for growth is a key KPI for survival, but most businesses are seriously in debt. But they can't expand easily now without going further into debt. So corporate culture in this environment is going to struggle to survive. What I'm saying is it will evolve into something else as a social structure. This is the fate of our current industrial management system as I see it. If we were having this discussion 50 years ago, that may not be the case, but we're not. And that's not the end of industrialization, it's just the end of doing it this way. This is a bronze statue on the banks of the Brisbane River. When it was installed, it was considered very controversial because most people didn't get it. Makes perfectly sense to me. All of our current efforts are pushing in the wrong direction and are ultimately irrelevant. Now, how will this all pan out for the mining industry? The ethics of what gets used and for whom becomes highly relevant. Let's say person A and person B want the same pallet of aluminium ingots. Person A wants to build a roof over his swimming pool at his holiday home and has lots of money. Person B wants to build a series of water bore pumps in a region with drinking water shortages, but also represents a nation-state government where that resource is situated. Now, in the good old days, the person with lots of money gets the goods. Too bad, so sad, move on. But what happens if what we call money has become really unstable? And what happens when the have-nots outnumber the haves? They now understand certain things that they didn't 10, 20 years ago, and they're getting very angry. How will it work? This will be democracy in action. Grab your pitchforks and burning torches, it's time for a visit to the castle. Now, professionally, when you get up and sort of tell people about a problem, you must put up a solution or you get shot in the head. That's just the way it works. So what will the mining industry actually do? Where do we put the good stuff? For the last 150 years, we dug up all the high-grade deposits, processed it, turned it into stuff, and threw it away into nice, convenient piles around our major cities. The future of mining is to go and mine our rubbish tips. And to stick the boot in, let's say you've got a ton of printed circuit boards. Right, in this case study, a couple of 100 grams of gold, a couple of 100 grams of silver, a couple of 100 kilograms of copper and aluminium, where your average grade of ore coming out of a mine site is around 1 gram a tonne of gold and maybe 10 kilograms of copper. And that's considered high grade now. And you've got a strip ratio to get there. So when you lot are finished playing with the World of Warcraft, donate your motherboards. Now that we understand that, we can start looking at what this all means. I use network theory to actually bring everything together. We've got raw materials, heavy industry, manufacture, just-in-time supply grid and retail. And at the centre, we've got energy and money. The same model could be applied to anything else, and a very small number of companies facilitate that network. So network theory, what can it tell us? Connections are paths where that everything links up, and nodes are where paths connect. For example, we all need petrol to function. We all go to a petrol station. So let's say we're looking at, if the network is damaged in a macrostructure term, it shrinks. Let's say Adelaide was hit by a power shortage in one suburb. You still have electricity functioning in Adelaide, just not everywhere. But if a node is knocked out, anything attached to that node unravels. So if disruption of that node is long enough to prevent a vital part of the network to function, the whole network is put at risk. In terms of industrial procurement, if you're going to build an industrial plant, say in South America, it's built in China. Parts of it will come from Germany and the engineering will be done in Australia. We need industrial procurement and currency transfers to make all that happen. But what if we were to disrupt the United States and the European Union as places to do business? That network would unravel, and the only one standing would be China. So, if the network is necessary, and a new one will manifest in place of the old one according to a new set of rules, it will be so because it's necessary. Energy is the controlling parameter. It controls the size of the network and the density of network. It comes down to the density of the energy involved. And our energy is supported by cheap, abundant energy, oil. Let's say we had a cubic mile of oil, or about a year's demand for oil. If we were to take that off the grid and replace it with an alternative system, we're talking about 104 coal-fired power stations every year for 50 years, 52 nuclear power plants each year for 50 years, 91 million solar panels, or 32,000 wind turbines. We don't have an energy source dense enough to replace oil. A complex system is not made in situ. You've got to grow it from a simple network over time. What it all means, peak oil is the node of petroleum energy and is about to be disrupted. All links to that network system will be logistically traumatised, and as it stands, any replacement system has a less dense per unit volume and requires infrastructure to be built, which will take time, and this means the replacement network will need to be less complex than the current one and will take time to reach that complexity. Same thing will happen in a few years for gas and in 10 years' time for coal. So, what drives us? Someone actually asked me this, why is this allowed to happen? Social institutions are based around what is possible. If cheap, abundant energy is our engine, then mining is the gearbox, but our environmental carrying capacity is the brakes. But environmental degradation and population overshoot really are problems that we can't negotiate around, and we're approaching them really, really fast. Now, these pictures here describe our current corporate culture. A lot of people get upset by that, but that's the reality of it. One small group of people in one part of the planet get rich at the expense of lots of other people on the other side of the planet. And so someone asks, how did this happen? Why are we allowed to do this? And the simple answer is because they could. And we never understand the true consequences, and we were convinced it's okay. A small number of people a couple hundred years ago said, come with us, we'll make you rich. They did, and it did, so it all worked out fine. But a case can be now made that the corporate culture, the exploitative nature of corporate culture, is now applying those problems not just to people in third world countries, but now to us. The CSG debate is relevant there. So corporate culture has now exceeded its carrying capacity of its environment. It will change. Socially it must. I can say this from someone working in corporate culture. Expecting it to do the right thing for the people on the ground really is a waste of time. They're just not that way. For a start, anyone who talks about something that might threaten their business model or incur loss is dismissed. But once survival becomes an issue, we're going to see some very choice behaviour. After 15 years working in the mining industry, this is what I've come to conclusion. You can't make a system change that doesn't want to, that regulates its own authority and it has its own political power source. But you can be at the right place at the right time when that system breaks. And yes, it's breaking. Conventional thinking has no hope, but unconventional thinking and asymmetrical strategy certainly does. Timing is the key to everything. Now, we've got some very challenging information in front of us. Everyone should try thinking for themselves at least once. Try it now.